to the last session of today by Professor D Kundu in a different topic, bivariate distributions with singularities. Professor Kundu, please.
Yeah, okay, good afternoon again. Welcome back. And well, this one is a completely different one, which is the bivariate distribution with singular component. And this is the one I got interested a few years back. So I thought it's interesting. Okay, so let's share it with you. Okay, so let's see. What do you mean by that with singular component, and what is the difference with the usual bivariate distributions, what we know actually. Okay, so I'll start with some motivations. Why do you need this? And with an example, of course. And then we'll go back to this, one of the most famous one, which was started, I would say the starting point of this bivariate distribution with singular component, which is the Marshall-Olkin bivariate exponential. And I think that was the starting point. And they had proposed this particular one, and after that there are lots of modifications, generalizations which has taken place, and this is one of the most used one, which is a generalization of the Marshall-Olkin bivariate Weibel, and we'll talk about the bivariate generalized exponential. But what I think is important, and I think which is different than this one, we'll see this one that all these things can be put into one framework using what is called copula, okay, which is becoming extremely popular nowadays. So we'll see this one that although they arise in a different ways, but they can be put together using this copula functions. Okay, so we'll see how does it work. I think that is one of the nice part about combining different distributions. I'll skip about the inference part, but that is also very interesting, by the way. Both these Bayesian as well as the classical inference. I'll skip that one. Those who are interested, please come and talk to me. I'll be very happy to do this one because, those are also quite nice actually. We'll see this one that how we can use this efficiently, all this EM algorithm and all these things, and things can make it very nice. Okay, so so see when this Marshall and Olkin had started this one, 1967. Of course, the EM was not there, so implementation of that one was not that easy. Okay, so but now things are much easier. Okay, so let's start with this example, two examples. So this is a data which basically shows. By the way, all these data, there is a extremely huge collection of data of the soccer game, which are available in the UK soccer site. Okay, so you can go this one, you can see this one. It's a huge amount of data which are available. Of course, they are all free. They have each match by match, and they have several forms of data. So this has been collected from one of those sites, and they have a very specific reason also. I'll come back to this one. I'll first let me explain the data, and then I'll come back to this one. Why they keep those data? Where they use those data, particularly the data of this type. So this is the data. What it shows that the first number, you have a home team, of course, where the game is being played, and the opponent which came to play into that particular field, and the data shows this one that the first team, the home team, scored the first goal, and here the opponent scored the first goal in minutes. Okay, so in the 5.35 minutes, the home team scored the first goal, and 35.43 minutes, the opponent scored the first goal, and blah blah blah. Okay, and of course, here the data are truncated in the sense we have collected those data, or rather we have proposed those data where at least both the team have scored at least one goal each. Okay, so that's the reason this one that's what it is. Okay.
This is actually 4 different matches.
Yeah. 4 different matches of this at the home team. Yeah, exactly. And 4 different opponents. They're not the same opponents also. They're different opponents. Yeah, because this thing is fixed. This thing is that home team is fixed, but the opponent is different. Yeah. Okay. So they are trying to get this one. Okay. By the way, actually, these data are being used quite a bit by all these TV channels. By the way. Okay. So because they try to put their advertisement on all these things depending on these things. So that's the reason this one that these are the data has lots of this commercial value. I mean, people do use these things in the commercial setup. Okay. The second one, which is slightly different. The second set says the first number indicates the time at which the home team scored the first goal. Again, it's a truncated data that where the home team at least scored 1 goal. So the home team scored the first goal. And the second number indicates the time at which the first kick goal took place. Well, what is a kick goal? Kick goal basically means that which one you do the goal directly, which is basically by the direct free kick, penalty, corner kick, things like that. Okay, so which is not by passing. Okay, and one of the reasons this one that these things are important because actually these are the things which are spectacular. Okay, I mean, for example, I mean making a goal by the free kick one. Spectacular, making a goal from the corner kick, like the Botham used to do. So those are the things, those are quite spectacular one. So they also collect this kind of data. Okay? Yes, so that's the reason I'm saying this one. See what it says. The first one says, is the kick, the home team scored the first goal here. And this one says, the second indicates the time at which the first kick goal took place. So that means this goal, so the first goal was kick goal itself. So the home team has scored this first goal at this point, and that was the first kick goal itself. So in this case, we do not have the data. I don't care whether this one, whether the second team has scored the first goal any time or not. That we do not have the data. But what we have, the first kick goal took place at this point, so it is clearly the same as the home team. So home team, the first goal, they make it as a kick goal. That's what it is. Okay, fine. Same thing over here. The home team scored this goal. And the kick goal took place as this one, so clearly the opponent make this goal. That is clear. Again, same thing over here. The home team scored the first goal at this point, and that is a kick goal. That's for sure. The home team scored this first goal, this one, so opponent clearly scored this goal. So you can see that I have 2 different sets of data. And in fact, Ashok has mentioned this one, which I'm trying to say. So what is the major difference between the two? What is the major difference between the 2 sets of data? You can see this one that we can assume that both the marginals are continuous. I mean, let's assume this one is a 0 to 90, but let's make both the marginals to be continuous in both the cases. In this case as well as this case, that part is okay. But what is the major difference between the 2 sets of data? The major difference between the 2 sets of data is that there is a positive probability that the 2 components can be equal. There is a positive probability. You cannot ignore that part. Okay? As we had mentioned, as we are saying this one that, so that is precisely what we are looking for. That means I have a positive probability. It is not by chance or anything. Definitely have a positive probability that X can be equal to Y. That's what it is. Okay? So that is the main difference between the two sets of data. So both the marginals are continuous. Let's assume this one. That's not a big deal. In the first case, there cannot be any ties. For sure, because the first team scored the first goal, the second team scored the first goal, so clearly there cannot be ties, whereas in the second case, there is a positive probability of ties. Therefore, the usual bivariate distributions, what we are familiar with, bivariate normal, bivariate log normal, bivariate, all these things, it's not possible. You cannot use those things to analyze this kind of a bivariate data. Okay? So that is the whole thing. That is the whole moral of the story. That's what you want. So these are some of the very, very standard bivariate distributions. If you look at the bivariate normal, clearly probability x is equal to y is 0. Same thing with the bivariate log normal, probability x is equal to y is equal to 0. Bivariate inverse gamma distribution, which is also same thing, and the bivariate Birnbaum-Saunders, which is becoming quite popular nowadays, but still it's an absolutely continuous, so probability x is equal to y is equal to 0. So we cannot have that. So we need something else. Okay? So we need something else to model these things. So Marshall-Olkin bivariate exponential, I think as I mentioned, this is the first time they had proposed a model of that type where you can have probability x is equal to y, which is strictly positive. It is not equal to 0. That's what it is. And so how they have arrived. Idea is very simple. Idea is a very, very simple one. I mean, again, I mean, that's what everybody says, this one, that when some idea is very simple and it has been implemented, and then actually it can make it more popular. And that is precisely, I think, one of the reasons. It's a very, very effective model, and it becomes a very, very popular model by that way. It was introduced in 1967, but still it is being used in different forms. Yes, please.
Could you go back to
Sure.
where you said the absolute continuous BVA
Yeah.
could not be used? The previous one.
Yeah.
Yes. So could you explain?
Oh, why did I say? I said this one. See, here. That's what I'm giving these two examples. So, is this clear? Is this clear? That well. So that means what we can see this one, that if I have a data, suppose I give you a data set of this one. Okay, I know this one, that this probability, these two are equal. It is not by chance. There is a positive probability. So now, if you try to use a bivariate normal here, it does not make sense. Are you getting my point? Because I know that in case of the bivariate normal, probability x is equal to y is 0. So definitely, we should not use bivariate normal here, because I know that probability x is equal to y is not equal to 0. Okay, fine. So it is not by truncation or not by anything else. It has happened with a positive probability. I know this one, that it can happen with a positive probability. Okay, fine. Is that clear? Okay, so that is precisely what I am trying to say, that well, I mean, the main difference between these two, here I know this one, that probability x is equal to y is 0. It cannot be equal. But in this case, there is a positive probability, and therefore for this reason, I cannot use the sum of the standard bivariate absolutely continuous distribution, where I know that probability x is equal to y is equal to 0. Fine? Okay. So that's the reason that we have to go beyond that. Okay? And that's what this Marshall and Olkin has introduced. And as I said, the idea is very simple. And how they have started? They have taken 3 exponential random variables, x1, x2, x3, that are independent. Okay? So 3 simple independent exponential random variables with parameters lambda 1, lambda 2, lambda 3. Okay, let me be specific, because whenever we talk about the exponential, it can be mean or 1 by mean. So what we mean by that, we basically mean that the density function, the probability density function of the exponential, which is lambda e to the power minus lambda x, which basically means the mean is 1 by lambda. Doesn't really matter, but anyway, let me be specific. So the mean here is 1 by lambda, and the distribution function is this one. So that's what it is. So all this lambda 1, x1, x2, x3, they have this lambda 1, lambda 2, lambda 3. Now, what they have proposed? They have taken a very simple one. They have taken x, which is the minimum of x1, x3, y, which is the minimum of x2, x3. That's the way they have proposed. Okay? Now, let's look at this one. So this, when you put this minimum of x1 and x3 and minimum of x2 and x3, so the natural question comes, why minimum? Why not something else? Okay. One of the intuition, of course, we'll come back to some of the nice physical justification also. But I think physical justification came later. That's what I feel. Okay. I think one of the main reason I think they have chosen that, because again, if you look at to exponential, minimum is also exponential. I think that is the reason they have chosen it. That after that they come up with a very, very nice physical interpretation. That's what I think. Same thing over here. So the minimum basically, so the exponential is closed under minimum. Exponential is closed under minimum. So what you can see that your x and y both are exponential. That's what we have. But definitely, what we'll see here, that probability x is equal to y is actually not 0. Okay, and that's what we'll see. That's what we're trying to compute. What is my probability? X is equal to y. We'll do this one. But let's now come to this, the physical interpretation. I think, as I said, I think that once you develop the model and then you try to come up this one. Fortunately, in this particular case, it turns out to be very nice. Okay? It has a very, very nice physical interpretation also. And it comes up in terms of the Poisson process. Okay? So let's go back. Let's go back and just let's recollect what is the Poisson process. It's a very simple one. Basically, first I'll define what is a stochastic process, which is a collection of random variables. Okay? I specifically mention not necessarily a sequence of random variables, which basically means that this is uncountable in numbers. I just want to emphasize that. Okay? So basically, it's a process for t greater than or equal to 0. So it is not only a countable, it's an uncountable number of elements in NT. Okay? So NT is called a stochastic process, which is just a collection of random variables. Of course, they are not independent. Because if there is independent, there is no point, there is no fun. Okay? So they are dependent. There is some dependent structure, we'll come back to that. So this is a stochastic process. I called a stochastic process to be a counting process if it simply represents the total number of events that have occurred up to the time point t. So that's the only thing what I need. Okay? So I call this one as a counting process if I have a stochastic process and I just look at how many events have taken place up to the time point t. Okay, so now let's look at what is the properties of a counting process. It's very simple because I know that I'm looking at the number of events which have taken place, so clearly my nt has to be non-negative, nt has to be greater than or equal to 0. Nt, I'm looking at the numbers, so nt clearly has to be integer valued, no problem, that is also there. And since it is gradually increasing, so I know this one that if s is less than t, clearly my ns has to be less than or equal to nt. So it's an increasing process or rather non-decreasing process. And so this is one of the important things what I need, that s less than t, that means nt minus ns denotes the number of events that have occurred in this one. Okay? So that's the way I just denote this one. Now let's look at this. What is a Poisson process? Poisson process is simply nothing but a counting process which satisfies these things, that my n0 is equal to 0. So at the beginning, there is nothing. The process has independent increment. I need this one, which simply means that, well, I know this one, I had given an interval, and I know this number of events which has occurred in this interval. I take another interval, I look at the number of events which has occurred in this interval. So now if these two intervals are disjoint, so the number of events which have taken place, they are independently distributed. That's the only thing what I need. Okay? So this process has independent increment, that's what we mean. So if you have a disjoint intervals, then the number of events which have taken place during those intervals, they are independently distributed. That is there, and it is called a Poisson process if your nt plus s minus ns, which basically means the number of events which has taken place between s to s plus t, that means the length is t, so it does not depend on s, it just depends on t, so it is Poisson lambda t. That's what it is. Okay, so it is called a Poisson process if it satisfies these three properties. Now, what it says, if you look at this, going back to the Marshall-Olkin model, it has another name which is called a shock model. Okay, and the reason it came, it says this one, the shocks come according to independent Poisson process. So basically, the three shocks are coming. Okay, we are assuming that there are three shocks which are coming. They are coming as an independent Poisson process, each one of them separately. The first shock affects component 1. So we assume that the system has two components, okay, component 1 and component 2. So the first shock, so the shocks are coming as an independent process, Poisson process. The first shock affects the component 1, the second shock affects component 2, and the third shock affects components, both the components. So the first one affects the first one, the second one affects the second one, third one affects the both of them. Okay? So a component fails as soon as it receives a shock. So either it can be 1, it can be 2, or it can be 3, depending on that which one it is, which component it is. The first component can receive the shock from 1 and 3, then it fails. Similarly, the second component, if it receives the shock from 2 and the 3, then it fails. So basically that means what it boils down, if x1, x2, x3 denote the time at which the first shock, second shock, and the third shock arrive, the lifetime of the components 1 and 2 are x is equal to the minimum of x1 and x3, and y is equal to minimum of x2 and x3. As simple as that. So basically that, it has a nice interpretation in terms of the Poisson process. Okay? The reason actually I had described this one, because we'll see this one that when you move to the second one, which is a Marshall-Olkin bivariate Weibull distribution, there we'll see this one that it has a nice connection with the renewal process, okay? Which is a little bit generalization of this Poisson process, nothing difficult. I'll just explain, it's very simple, but it has a nice connection with this shock model. So that's the reason this one that this is called a shock model. Okay, so now let's look at a couple of things, okay? These are the very simple one. If you look at x, which is exponential lambda 1 plus lambda 3, just because simply is a minimum. Y, which is also lambda 2 plus lambda 3, because it's a minimum. If you look at the minimum of x and y, which is also exponential lambda 1 plus lambda 2 plus lambda 3. It's a very simple observation, but it's a useful observation actually. Okay, so these three will play important roles in the data analysis one. Okay, so that's what it is. Okay, now let's try to compute some of the things, and I will go through in an explicit manner, and I thought that it's worth doing it. There is no harm. So let's calculate what is the probability x is equal to y. So if you try to look at probability x is equal to y, so how it can happen? What is my x? X is the minimum of x1 and x3. My y is the minimum of x2 and x3. So that means probability x is equal to y, it can happen if your x3 is less than x1 and your x3 is less than x2. Then that's the only way your x is equal to y can happen. There is no other way it can happen. Okay? So because whenever your x is equal to y, that means both of them has to be equal to x3, which basically means your x1 has to be more than x3, your x2 also has to be more than x3. So basically probability x is equal to y, which is probability x1 greater than x3 and your x2 greater than x3. So now if I write this one, which basically means that x3 is less than the minimum of x1 and x2. Okay, fine. So now what is this one? That is very simple, because how do you compute this one? So let's put the density function of x3 at the point x, which is lambda 3 e to the power negative lambda 3x. I know this one that x1 has to be greater than x3, which is simply nothing but e to the power negative lambda 1x. x2 also has to be greater than x3, which is e to the power negative lambda 2x. X can be between 0 to infinity, so which is simply nothing but this one, which is simply nothing but lambda 3 divided by lambda 1 plus lambda 2 plus lambda 3. So you can see that probability x is equal to y, which is simply nothing but lambda 3 divided by lambda 1 plus lambda 2 plus lambda 3. This quantity is not negative as long as your lambda 3 is not negative. Okay, fine. Okay. Let's look at the survival function. And I think that is going to play an important role. So let's try to look at it explicitly, carefully. Okay, so what is the survival function? S of xy at the point xy, which basically means probability x is greater than small x, my y is greater than small y. Fine, okay, that's what it is. Which basically means probability x1 is greater than x, because x is the minimum of x1 and x2, x1 and x3, my y is the minimum of x1 and x3. So the minimum is greater than x, so that means both of them have to be greater than x. So x1 has to be greater than x, my x3 also has to be greater than x. Minimum, so x2 has to be greater than y, and my x3 also has to be greater than y. So therefore x1 has to be greater than x, x2 has to be greater than y, and x3 has to be greater than the maximum of x and y. Okay, because x3 has to be greater than x, x3 also has to be greater than y, so x3 has to be greater than the maximum of x and y. Exactly the same calculations. If you look at x1 is greater than x, x2 is greater than y, x3 is this one. They are all independent, and therefore simply the product of the three, so which is e to the power negative lambda 1 plus this quantity is e to the power negative lambda 1 x, this quantity is e to the power negative lambda 2 y, and this quantity is nothing but e to the power negative lambda 3, the maximum of x and y. Now, if we split into two, that means that if your y is less than or equal to x, so the maximum of y and x is x, so that means it is getting added with this one, and if we take y is greater than x, so this quantity, the maximum of the x and y, so it is added with. So what we have, the survival function, the joint survival function, which simply comes out in the two different shapes. Okay, so that means for one is y less than x, another is y greater than x. And of course, if you have the joint survival function, you can always get the joint distribution function also by using these simple relations. Okay, so that's not a problem at all. Okay, let's look at this quantity. That what do you mean by that? The absolute continuous cumulative distribution function or the absolute continuous survival function. Let's go back to our basic definition. We know it one dimension. Let's look at two dimensions. And so if you look at, I call that a distribution function is an absolutely continuous distribution function if there exists an f of uv such that f of uv is greater than or equal to 0 and f of xy can be written in this form. Okay? Any joint, any bivariate distributions, this is a cumulative distribution function which is in this form. Exactly the same way, if I look at the survival function, same thing, there exists an f of uv such that f of uv is greater than or equal to 0, then it can be written as x to infinity, y to infinity. So I will call a distribution function, a bivariate distribution function is absolutely continuous if I can find an f of uv which is in this form. Similarly, a bivariate survival function I'll call is an absolutely continuous and equivalent if there exists an f of ub which is in this form. Okay, so fine. So that's what we have. Now let's try to recover that. Okay, that means that if I have this capital F of xy, how can I get this small f of uv? Or if I have this capital S of xy, how can I get this small f of uv? That's simple. Simply take the double derivative of this one and you will be getting this one. And that's what it is. So because it's in one dimension, if you look at it, you take a single derivative. And in this case, there is a negative of the single derivative, but since it's a bivariate case, so both the cases I can get by f of xy by the double derivative of this quantity and the double derivative of this quantity. There is no negative sign because negative becomes positive. So that means if I give you capital F or if I give you capital S, I should be able to recover my small f by taking the double derivative. Now let's see in our case what is going to happen. Okay? So let's try to recover this f of xy from our joint distribution function, or rather joint survival function, what we had given. So what is my f of xy? As I said, it's a second derivative of s of xy. You go back to the definition of this s of xy. It's a very simple one. That's what it is. So if you take the derivative of this quantity with respect to x and y, you can easily get it, and you just have two different components. That's it, nothing more than that. So that's what you'll be getting it here. So that's what you are getting it for y less than or equal to x, your f of xy, which is in this form, and for y greater than x, which is in this form.
Sir,
Yes, please.
just a simple question.
Yes, please, go ahead.
Do you not need any assumptions on small f?
I just need the assumption that small f has to be greater than or equal to 0. That's it. That's the only assumption I need. I mean, I'll say this one, a distribution function is absolutely continuous if I can find a small f, such that my small f is greater than or equal to 0, okay, and this thing is satisfied. That's the only thing I need. Or of course, I mean, whenever I'm putting over this one, they are integrable also. Yes, of course. I mean, most of the time is a continuous, but yeah, integrability is fine. Okay, so that's what basically I need, nothing more than that. Okay, then only I'll be calling this one as an absolutely continuous. Is that fine? Okay, fine. So that's what I need. Okay. Can I proceed? Is that okay? Is that fine? Okay, yeah. So let's come back. Let's try to recover this small of f of xy in our case. Okay, in our case, I have this joint survival function s of xy, and I'm trying to get this small of f of xy by taking the double derivative. As I said, it's a very simple one. For y less than or equal to x, if you just take the derivative, you'll see this one that, say, these things are nothing but the exponential with parameter lambda 1 plus lambda. So this small f, which is nothing but the exponential with parameter lambda 1 plus lambda 3, I think I had mentioned it at the beginning itself. When I put this exponential density function, yeah, here, the same f. It is the same f actually, okay? So it is, instead of lambda, it is lambda 1 plus lambda 3, or lambda 2 plus lambda 3. So it is basically the same f I'm talking about, okay? So which is an exponential density function. So that's what it is. Here I have, yeah. So here I have an exponential density function which is lambda 1 plus lambda 3, an exponential density with lambda 2 for y less than or equal to x, exponential with lambda 1, and exponential with lambda 2 plus lambda 3 for y greater than x. So that is a joint density function of f of xy. Okay, I just got it by taking the double derivative, but let's go back and let's see this one, that whether it is satisfying that property or not. Okay, so whether your capital F or capital Y, they're satisfying. So one of the simple thing, let's look at integration over the entire range. So let's look at the integration over the entire range, this f of xy dx dy over the entire range, and actually it's very easy to see because if you just put this integration, put this form, which is lambda 1 plus lambda 3 e to the power lambda 1 plus lambda 3x, lambda 2 e to the power negative lambda 2y, if you simply do this integration, it's a very simple integration, exponential integrations, nothing more than that. You'll come up with lambda 2 divided by lambda 1 plus lambda 2 plus lambda 3, and the second one will give you lambda 1 divided by lambda 1 plus lambda 2 plus lambda 3. So you can getting it lambda 1 plus lambda 2 divided by lambda 1 plus lambda 2 plus lambda 3, which is less than 1, which it should not be. Okay, so clearly I cannot get back my small of f of xy from the capital S of xy, the joint distribution function, okay, because which is strictly less than 1. Reason is very simple, because what we have seen this one that I have on the x is equal to y, okay, and that's what we'll see now. So clearly it is not an absolutely continuous distribution function or the survival function. Clearly not. Okay? So now let's look at this particular case. What is the probability that x is greater than or equal to 0 and y is greater than or equal to 0? Let's look at that. So these things I should be able to split it up: probability x less than y, probability x greater than y, probability x equal to y. Naturally, because that's what I'm looking at, the whole component, the whole space. So this is less than y, this is greater than y, this is equal to y. And in fact, these two, if we combine these two, which is simply nothing but the integrations, whatever we have shown it before, this particular integrations, what we have, probability x greater than y and x less than y, and I have left with this separately, and that is precisely what I'm getting it here. So if you look at the entire one, I'm getting it 1. So I have in this extra component, which is playing the problem, okay, which is not the usual one, what we see in the usual bivariate distributions. So now let's look at, say what I'm trying to do. I'm trying to obtain a joint probability density function, okay, in some sense, okay, and that is precisely what is my aim, because what I have seen this one, that a joint probability density function does not exist because it is not an absolutely continuous survival function or the distribution function. So, but can you get it in some sense? We'll come back to this one, and that is precisely what we are trying to do, what we are trying to get. Okay, so what I'm trying to do, I'm trying to look at probability x greater than or equal to a and y greater than or equal to a. That's what I'm trying to look at it here. And well, again, I'll split it up into two parts: probability x greater than a less than y, probability x greater than y greater than a, and probability x equal to y greater than a. Okay, if you look at this quantity, which is simply nothing but this one, if you look at this quantity, which is simply nothing but this one, if you look at this quantity, which is simply nothing but this one. So this one, which is this quantity, this one, which is this quantity, and this one, which is this quantity. So let's compute. Let's compute this one. So, well, I mean, yeah, I'll compute this one, but so which basically means that the probability x is equal to y greater than a, which is simply nothing but this quantity minus this minus this. That's what it is. Because I have this quantity. I already have that quantity in my s of xy. This quantity I have, and I have this two quantity also. Okay, so that's what I have. So probability x is equal to y greater than a. So this minus this minus this. Okay, so far so good. So now let's try to compute. Yeah, there is a mistake here. This should be e to the power. So probability x greater than or equal to a, y greater than or equal to a. So this simply comes out from this s of xy that we have here. So this s of xy, if you put x is equal to y is equal to a, you'll be getting both of them are same, which is e to the power negative lambda 1 plus lambda 2 plus lambda 3 a, which is precisely what this quantity is. Which is precisely what this quantity is, that the probability x greater than or equal to a, y greater than or equal to a, which is this one. If you calculate this one, probability x greater than a less than y, which is from here, this particular integrations, actually you'll be getting it here, lambda 1 divided by lambda 1 plus lambda 2 plus lambda 3 e to the power negative this quantity, same quantity. Similarly over here, probability x greater than y greater than a, lambda 2 times e to the power, same this quantity here. Okay? So what we get, probability x is equal to y greater than a, which is simply this quantity, which is simply nothing but this one. So I try to write this quantity in the integral form, and you'll see the reason for that. So probability x equal to y greater than a, which can be written in this integral form, which is nothing but this quantity. Nothing but this quantity, which is I have just written in the integral form. This one is the exponential density. So now, what we can see, I'm just going back to my survival function, s of xy, which is probability x greater than x, y greater than y, which is the first one, which is already there, which you have already seen. But I have the second one, which is probability x is equal to y, which is greater than a, which is this quantity. So this is the one I am trying to use it to give a new definition of the density function of this s of xy, and that is precisely what it is. So now, what it says that, well, what it says this one, the Marshall-Olkin bivariate exponential has the joint PDF with the following structure. So that means for x less than y, which is of the same form this f of uv for x less than y, and on the path x is equal to y, it has this particular density function, and that is precisely what it is being written here, f1 xy for y less than x, f2xy for y greater than x, and f naught x for x is equal to y. So this is a slightly different way, different interpretations, not the usual one. In the measure theoretic term, what they call that? Well, I am talking about this particular density has a two-dimensional Lebesgue measure on this plane, and it has a one-dimensional Lebesgue measure on x is equal to 1. Nothing more than that. But what is important here, that well, if you use this particular function, you can recover your s of xy. That's the whole thing. That's the whole idea about this. So you should be able to recover your, these are the form of the 3f1, f2, f0. And well, I mean, that what it basically means, let me just mention it once more, that if you're trying to recover my s of xy, I should be able to use this particular integrations, f of this particular function, f of xy, this one, such that I have to integrate on this range, I have to integrate on this range, and I have to integrate on this particular line, x is equal to y. That's what it is. Okay? That's the reason that it is called a joint PDF in that sense. Okay? Not in the usual sense, but the joint PDF in that sense, because one is 2 dimension, another is 1 dimension. Yeah, this is the form. Let's look at a couple of pictures. Well, this is one of the standard picture. What we'll see, it will be always a decreasing function, just like the exponential distribution. Exponential distribution is always a decreasing function. So here also, it will be always a decreasing surface. Okay? So, well, let's look at a couple of simple properties of this one. The joint survival function has the following unique decompositions. Well, this is actually true for any distribution function. Okay, it doesn't really matter, because any distribution function you'll be always able to write it as an absolute continuous one and a singular one. Okay, so in this particular case, I can get those things in the explicit manner, because I have this quantity. I have this s of xy. I have this singular one, and I can use that one to get the other one. So that is precisely what it is, a singular component, which is nothing but in this one, the exponential one. And I have this absolute continuous one, which is this minus this. Okay, so I can get back those decompositions in the unique manner. Again, if you look at the density function also can be written in this unique manner. So here it is a 2-dimensional one on x and y, and this is the 1-dimensional one which is on the line x is equal to y. Okay, that's what it is. This z is nothing but the maximum of x and y. Okay, so this is the joint density function. That's what we'll be calling it from now on. Some of the simple properties which can be easily derived, as I said, because it's a simple model, it can be easily derived, because if you take lambda 3 goes to 0, then your survival function, because lambda 3 goes to 0, it simply converges to this one, which basically tells you that your x and y becomes independent. That is precisely what it is happening, comes out as a product, and so that's what it is. So your probability x is equal to y becomes equal to 0, because lambda 3 goes to 0, so this becomes equal to 0, and they turns out as a product, so they turns out to be independent actually. Okay, that is one of the nice part. And if you take lambda 3 goes to infinity, keeping of course lambda 1, lambda 2 fixed, so probability x is equal to y, which is nothing but this one, which goes to 1. Okay, so which basically means that the correlation, okay, it always lies between 0 and 1. So this is one of the general problem what we find if you try to have a non-negative random variables and you are trying to have a bivariate distributions. So you usually get the correlations either 0 to 1 or minus 1 to 0. Having on the entire range is not very easy unless you go with the copula 1. I'll be talking about that maybe later on. Okay, when you're talking about that copula 1, that is. But otherwise, if you try to do it this way, it is not possible. Okay. Yeah. So I'm coming to this the copula 1, and which is well, it's an interesting way of looking at the bivariate distributions, and it is becoming extremely popular. The reason is that because I think, of course, it has lots of nice theoretical properties, but I think one of the major reasons is that in the high dimension, if you have this copula, if you try to use the copula, your computation becomes extremely simple. Okay, computation became extremely simple, and that's the whole reason about using the copula. For example, I'm just giving an example before going into the detail. What it says that, well, I mean, let me just briefly mention, and then I'll come back to the detail. Copula basically gives you a measurement between the different marginals, okay, the dependence between the different marginals. So what people do in the data analysis, they try to model the marginals first, okay, and then they use some kind of a copula to model the dependence, okay, and that actually makes the thing simpler because it breaks up into two components, okay. One is the marginal, another is the interdependence structure, okay. So we'll see how does it use, how it can be used. So what is a copula? Copula is nothing but a function which is defined on close 0, 1, close 0, 1 to 0, 1. Okay, which is nothing but a distribution function, by the way. Copula is nothing but a distribution function which is defined on 0, 1 cross 0, 1. So that means its domain is 0, 1 cross 0, 1. Okay, so any distribution function actually always can be written in this form. Okay, any distribution function can be written in this form, f of xy, which is the c of capital F of x, capital F of y. Okay. How can I get back my c? That is also very simple. I can get back my c from this capital F of xy, which is simply by using this form, that your c of uv, because I know that my uv is lying between 0 and 1, c of uv is nothing but your joint distribution function at the point f of x inverse of u, f of y inverse of u. Okay, so that is a simple form. So that means if I give you a joint distribution function, you'll be always able to get an unique copula. How to get the unique copula? You just get the unique copula from here. Okay, and you can see this one, that if I give you a copula, you can create millions of random variables, bivariate distributions. Why? Because you just choose different marginals. That's it. You just choose different marginals, and you can come back with the different distribution function. So because I give you the c, okay, suppose I give you the c, you just choose capital Fx and capital Fy. And that's the way. And this capital Fx and capital Fy are the marginals, and that's the reason that it becomes so popular, because you have a complete control of the marginals. Okay? And well, you can control your dependent structure through this C. Okay. So that's what it is. Okay. So let's look at, well, these are the couple of very simple example of the two copulas. I mean, which is nothing but, of course, your probability u less than or equal. Suppose u and v are two random variables defined on this 0, 1, as I said, because it's a proper distribution function. So nothing but your c of uv is simply nothing but probability u less than or equal to u, and capital V less than or equal to v. That's a standard definition of the distribution function. So clearly 0, 0 has to be 0, 1, 1 has to be equal to 1. And these are some of the very simple copula. Okay? This one is, of course, is not important, because this one is not that interesting, because this is independent. Two uniform independent, not that interesting, but this one is clearly dependent of this u and v. So this is definitely an interesting copula. So you can see that the interdependence between the two marginals are being modeled through this parameter theta. That's the way it has been done. Okay. How does it help? So, well, there is another called the survival copula, because it is not only the distribution function. The same way you should be able to write the survival function also clearly, because they have a 1-1 relation. So the survival function also, you should be able to write it in the same type, c tilde sxx sayy. So these are the survival function, and this is also another copula, by the way. So this c of uv, you can recover this c tilde uv by this way. Okay, so it doesn't really matter whether you are working with capital F or whether you're working with capital S, you can get the survival copula, and of course you have a nice relation between c and c tilde also. Okay, of course that's a relation what we have between c and c tilde. Both are copulas, and they have these nice relations between the survival and this one. Yeah, so copula becomes extremely popular, useful tool today, particularly in the high dimensional data and things like that. People are using it extensively. We can generate several distributions from a given copula. The interesting part is that many properties remain invariant. Doesn't really matter what kind of marginal distributions you put in, your final form many properties of the interdependent structure remains invariant, does not really depend on the marginals. It just depends on the copula. Okay, and well, as I mentioned again and again, the estimation becomes extremely easier when you use the copula compared to the usual bivariate distribution. So let's try to compute. Let's try to compute the copula in this. Oops. Yeah. So let's try to compute the copula in this particular case. So you can see that my S of xy in this particular case, which is simply nothing but this quantity and this quantity depending on the range, and your survival of x, which is simply nothing but that, survival y, which is simply nothing but that, and the copula C of uv, which is nothing but this quantity. So let's try to look at what is my C, and by simple putting the things, you can see that my Sx inverse, because that's what I need from the previous one, my Sx is this one, so Sx inverse I can easily compute. So Sx inverse, which is nothing but this one, Sy inverse, which is nothing but this one. So if you put it back into this one, so you can easily see that you can obtain my C of uv, which is in this form. Okay, so this is a copula of this Marshall-Olkin bivariate Weibull distribution. Let's rewrite this quantity in a slightly different way, or write this in a simplified manner. So if you can write this alpha, which is lambda 3 by lambda 1 plus lambda 3, beta, which is lambda 3 by lambda 2 plus lambda 3, your copula is simply turns out to be this one. Okay, so basically I'm just putting it, this quantity as beta, this quantity as alpha. I think that's what it is. Yeah, so this I put it this 1 minus beta, 1 minus alpha. So the copula, which simply takes this form. Okay, fine. And furthermore, if you put your lambda 1 is equal to lambda 2, if you put lambda 1 is equal to lambda 2, then your alpha becomes equal to beta, and that's what it is. So if you put lambda 1 is equal to lambda 2, and then your alpha becomes equal to beta, so your copula becomes this one. Okay, so your copula comes out to be very, very simple. Okay, so C of uv, which is in this form, that is the copula for the Marshall-Olkin bivariate exponential distribution. Okay, let's move to the Marshall-Olkin bivariate Weibull. What we are talking about, as I said, this becomes, of course, a more general version than the Marshall-Olkin bivariate Weibull, and well, idea is exactly the same, not much different. Okay, and we have a nice interpretation also in this particular case. So again, a Weibull distribution which has what is called the shape parameter alpha and the scale parameter lambda, which has this particular density function. And this is a generalization of the exponential one, and you can see that if you put alpha is equal to 1, then you get back to the exponential. Okay, and the reason it becomes so popular, because it has a nice, very nice distribution function, so it makes it very, very popular because it becomes very easy to use and things like that. Okay, so this is the probability density function, this is the cumulative distribution function of the Weibull. We do exactly the same thing. Okay, so I have x1, x2, x3. Okay, x1, x2, x3, they are independent, not identically distributed. Each one of them have the same shape parameter alpha, but they have a different scale parameter lambda 1, lambda 2, lambda 3, and I look at x, which is the minimum of x1 and x3, y, which is the minimum of x2 and x3. Idea is exactly the same. The reason is that I took the same shape parameter because then it is closed under the same distribution. So if you take x1 to be Weibull with shape parameter alpha, scale parameter lambda 1, x3 to be Weibull with the shape parameter alpha, scale parameter lambda 3, then x also turns out to be Weibull with the shape parameter alpha, scale parameter lambda 1 plus lambda 3. Same thing over here. Okay, so that's the reason this one, that the common shape parameter it's quite common. Okay, let's look at the physical interpretations, the way we have seen that the Marshall-Olkin bivariate exponential distribution, that we have modeled it using the Poisson process, how we can use it using the renewal process. What is the renewal process? The renewal process is just an extension of the Poisson process, and the renewal process is basically defined like this. Again, it's very simple. Suppose you have a sequence of independent, identically distributed, non-negative, continuous random variable. Okay? And basically what I'm looking at it, suppose I'm talking this one, I'm looking at this one as the lifetime of items. Okay? And I'm looking at it, how many items, and just think of this way, as long as something fails, I replace by another one. Okay? As long as something fails, I replace by another one, and with an identical equivalent item. So what I'm looking at it at the end of the day, I'm looking at NT, which is the maximum of n such that Sn is less than or equal to. That means how many renewals I need, how many items, new items I need till the time point t. That's what it is. That's what nothing but the renewal process is. Okay, so that's what the new process NT is. Well, actually you can easily see that your NT is a counting process because it increases. Okay, this is the number of components till the time point t, and all these things are there. Okay, so now what is the interpretation? Interpretation is that suppose the system has two components and there are three shocks which can affect the system. The shocks come according to independent renewal process where the inter-arrival distributions are viable. Okay? So in the case of the Poisson, the inter-arrival distributions are exponential. Here the inter-arrival distributions are viable and with the same shape parameter, but the different scale parameter, and same thing, exactly the same thing. The first shock affects the component 1, the second shock affects the component 2, and the third shock affects both the components, and a component fails as soon as it receives a shock. That's it. Okay? And in fact, you can see that if you denote this x1, x2, x3 as the time of the first shock, second shock, and the third shock, then your x is equal to the minimum of this, y is equal to the minimum of that. So you have a nice interpretation, even in this case also, in terms of the renewal process where your inter-arrival time is no more exponential, but a viable one. Okay? The same thing you can just go through, and you can easily see that the joint survival function, s of xy, which is probability x greater than x, y greater than y, I should be able to write it in this form. Very simple, exactly the same thing. Okay? And the joint survival function in terms of the joint distribution function, again, I have this nice relation, so I can easily get back that one. Go back to exactly the same way, whatever we have done in case of the bivariate exponential one, the way we have obtained the joint PDF. Here also I can get exactly the same way the joint PDF. It is not absolutely continuous. It has a singular part on the line x is equal to y, and I can write the joint survival function in terms of these integrations. One in the 2 dimensions, 2 of them are the 2 dimensions, one in the 1 dimension. Same thing. Okay? And this one also has a very, very simple, same expressions like this. Okay? So these are the viable density functions. It's exactly the same. It goes along the same line. These are some of the shapes of the joint probability density function. Now you can see that it can take an unimodal shape depending on the shape parameter alpha of this one. Okay? Yeah. So now if you go back, do the same calculations. If you go back to the same calculations, and if you look at the copula now, because you have the survival function, you can have the copula, exactly the same things you do, you can see that it has the copula which is of the same type actually, okay? Which is of the same type, the C of UB, which is in this one, which is exactly the same what we have in case of the Marshall-Wilkin bivariate exponential one, okay? And again, if you take your alpha is equal to beta, then you'll get back to the simple case. Okay, so it is. I have exactly the same copula what we have, what we had in the Marshall-Wilkin bivariate exponential. Well, these two, as I mentioned, I'm not going into the details about that. This is the classical inference and the Bayesian inference. Both of them are quite interesting, actually. Actually, what you can see that if you look at the classical inference, basically how many parameters it has 4 parameters. It has 4 parameters, so you can see this one that, well, to obtain the maximum likelihood estimators, you need to solve a 4-dimensional optimization problem. Okay, but we do not need to do this one if we use the EM algorithm. And the EM algorithm, let me give you the basic idea about the EM algorithm in this case. EM algorithm, the way it works, that well, you try to formulate the problem as a missing value problem. So you treat this problem as a missing value problem, so some of the things are missing, so you replace this one by the expected value, and then you try to maximize, and you repeat the process. What you do here, you treat this problem as a missing value problem, and the missing observations are basically one of the things. So if you look at the going back to the basic definition, if you're going back to the basic definition, which is the minimum of x1 and x3, the minimum of x2 and x3. So that means you'll be observing in this case only one of these. Okay? You're not observing the other one. So you try to put that one as a missing value. Same thing over here. You're observing one of these. You're not observing the other one. So you try to treat this one as a missing value. And what it can be shown that, well, if you put those things in the missing values in the likelihood function, then actually you can solve the problem very easily. Then you don't have to go for this 4-dimensional optimization problem. You have to just solve 1-dimensional optimization problem. Okay? That makes that thing very, very tractable. Okay? And that's what it has been used actually for this one. Okay? And the Bayesian one also, people have done quite a bit of flexible things, and one of the standard way to look at this one, they call this one as a beta Dirichlet prior, and doing these things can be done. Okay? So those who are interested, you can ask me, I gave this one. Yeah, this is the last one, which is a similar to the Marshall-Olkin bivariate Weibull, Marshall-Olkin bivariate exponential, but put it in a slightly different way. So this the generalized exponential distribution, which has a distribution function which is in this form. Okay? So which is also an extension of the exponential. As you can see, if you put your alpha is equal to 1, then it comes out an exponential one. So if you take any other alpha, of course non-negative, then it's a distribution function, but it is not exponential. And suppose you take this one as a distribution function, you can easily obtain the probability density function. There are lots of nice properties about this particular one, which has been developed actually. Okay? So if you try to use the same thing here also, so here again we are looking at, instead of the minimum, we are looking at the maximum. The reason is simple, because it is closed under maximum, nothing more than that. So it is closed under maximum, it is closed under maximum. That's what it is. Okay? So that's what you're looking at it. X is x and y, and here I'm taking the scale parameters to be same, the shape parameters are different, and I'm looking at this x and y. We go through the same process. There is not much difference. We go through the same process. We can do the same thing, but we have a nice some of the physical interpretations of this model. I'm not going into this one. It is which can be put it in the mathematical form, which says this is a stress model, which basically means that, well, whichever has the maximum stress, that is going to affect. And similarly for the maintenance model, so suppose I have a maintenance for one component, and the third suppose there are 3 maintenance. The first maintenance is for the first component, third maintenance is for both. Similarly like this, so similar models which we can interpret actually even in this bivariate generalized exponential. So I have a nice physical interpretation also in that case. Go through the same thing. Instead of survival function here, I can go through the distribution function actually here. So the joint distribution function, your capital F of x, y, so probability x less than or equal to x, y less than or equal to y, so which is probability x1 less than or equal to x, x2 less than or equal to y, because x is nothing but the maximum of x1 and x3, y is nothing but the maximum of x2 and x3. So the x is less than or equal to x means both x1 has to be less than or equal to x, x3 also has to be less than or equal to x. Similarly, y is less than or equal to y means x2 has to be less than or equal to y, x3 also has to be less than or equal to y. So that basically means that, well, your x1 has to be less than or equal to x, x2 has to be less than or equal to y, and x3 has to be less than or equal to the minimum of x and y. Okay? Now they are independent, so I just put it exactly the same form. So I have this probability x1 less than or equal to x. Whenever my x is less than y, so the minimum of x and y is x. So these things will add up with this one, and this thing remain unchanged. So this one will come here. And similarly, when x is greater than y, so the minimum is y. So therefore, it is adding up with here. It's exactly the same thing. So I have the joint distribution function. Again, I can write the joint survival function, which is exactly in the same form. Well, I go back to the same probability density function also, it is not absolutely continuous, so the joint PDF has the following structure, exactly the same way. Okay, so that's what it is, and yeah, these are the three cases. Okay, exactly like the same. Okay, so these are some of the shapes. If you look at this is basically the shapes of the joint PDF. Okay, these are the shapes of the joint PDF. I did not put it on the x is equal to y. This is the absolute continuous part, by the way. This is the absolute continuous part because I did not put the x is equal to y, which is on the line x is equal to y. There is no point in putting it here because this is the absolute continuous part, which is here. Same thing with the sum of the different parameter set. That's what they are. The shapes of the absolute continuous part of the PDF, joint PDF. Again, the nice part is that if you go back to the copula, in this particular case also, you can come back to the copula which is in this form. Okay? So again, if you put this one as same thing as before, so you can see that I have exactly the same copula what we have seen in the previous case. Okay? So that means they have the same copula, whether it doesn't really matter, whether it's a Marshall-Olney bivariate exponential, Marshall-Olney bivariate Weibull, whether you go ahead with the maximum one also, so they are giving that to the same copula. Okay, I think that is the nice part about this one. Okay, and some of the important issues, as I said, we have there are quite a bit of work on the classical inference. You are looking at the maximum likelihood estimators. Same thing. Here also you can see that it's a 4-dimensional optimization problem. We cannot do it explicitly. Okay, it is not possible. So well, again, in this case also the EM can be used. Okay, in this case also EM can be used, and then yeah, it definitely reduces the computations significantly. Okay, because finally it boils down to solve a 1-dimensional optimization problem. And I think we are almost at the end. Yeah, I think thank you. Okay, I think I'll stop it here.
Any question?